Today we're doing exponential growth and decay word problems. This is our second day in this set of notes. So for our first problem, it says the function f of t equals 30,000 divided by 1 plus 20e to the negative 1.5t describes the number of people f of t who have become ill with the influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. Letter A, how many people will become ill with the flu when the epidemic began? So when the epidemic first began, no time has really elapsed, so we'd be plugging in 0 for t. So I'd have f of 0, essentially is what we're calculating, and I have 30,000 divided by 1 plus 20e raised to the negative 1.5 times 0. And I know this is going to become e to the 0, and anything raised to the 0 power is 1. So this will become 1 plus 20 in the denominator, which will be 21. So I have 30,000 divided by 21. So for letter A, when I divide this out, I get 1429. So approximately 1,429 people were ill when the influenza first began. Letter B says how many people were ill by the end of the 4th week. So for letter B, this means we're substituting in 4. So I'm calculating f of 4. So I have 30,000 divided by 1 plus 20e to the negative 1.5 times 4. So I would kind of go in stages, or if you want to type this in the calculator all at once, that's fine. The way you have to type it is 30,000 divided by the quantity, open a parenthesis, and then 1 plus 20e, and then you got to raise it, and then you need to put negative 1.5 times 4 all in one parenthesis, and then you need to close parentheses. So when I do that, I get approximately 28,583 people. So in about 4 weeks' time, that's how many people were ill. Letter C says, what is the limiting size of f of t, the population that becomes ill? So we didn't really talk about this in other sections, but it's kind of common sense. Notice in a town, it says in a town of 30,000 people, so the limiting size is 30,000 people. That's how many people live there, so there can't be more people ill than 30,000 because that's the overall total. Notice that's also the numerator of your problem, so that's another way to kind of determine your limiting size. It's the top value. So the next type of word problems we're going to do is about Newton's law of cooling. So there's a formula that we have to introduce to you. You don't have to memorize this formula. I will give it to you. But what I will not tell you is what all the variables represent on a test. So that would be like the part that you have to know. So the formula is T equals C plus the quantity of T naught minus C e to the kt. So C is your room temperature. It's actually technically considered our cooling temperature, but if you think about it, an object sitting in a room that's 70 degrees, well, that's going to be its cooling temperature. It can only cool down to the value of the room. T naught is the initial temperature of the item. The big T over here is your ending temp. Little t is time. And obviously K, again, this is kind of like those direct variation problems where K is different for every single problem. K is something that you have to determine. K should be negative if the object is cooling. So, like I said, I will always give you this formula. What I will not tell you is what all the variables represent. So that's what you have to know. So let's go ahead and apply this word problem. So a cake removed from the oven has a temperature of 210 degrees Fahrenheit. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees. So letter A says use Newton's law of cooling to find a model for the temperature of the cake T after T minutes. So my ending temperature is 140. So your ending temperature should always be less. If you take an item out of an oven, it's going to be cooling down, so the ending temperature is less. Our room temperature is 70, and then it's plus the quantity of the initial temperature, which is 210, minus the room temperature, and then E, I don't know what K is, and we know our time is 30. So because we're using 30, that means every problem thereafter, our time is going to be in terms of minutes. So to kind of start solving this, I got to isolate E as much as possible. So I'd start by subtracting that 70 over. So I have 70 equals, and then I would want to do 210 minus 70. So notice that common mistake is students say those two 70s cancel. They do not. This has the quantity over here, so you cannot do that. So 210 minus 70 is 140. E to the 30k. Then I would divide both sides by 140. So I get 1/2 equals E to the 30k. And at this point I need to put it in natural log form. So I have natural log E of 1/2 equals 30k. And I divide both sides by 30. So I got a bunch of calculator work here. And when I do that, I get K is approximately equal to negative 0.0231. And as a rule of thumb, we want to use as many decimal places as possible for our K value because that will ensure a more exact answer. So for letter A, our overall model, they said they want it in terms of big T and little t. So I would say T equals 70 plus 140 e to the negative 0.0231 t. So now this is the equation that I can use for any given information. So notice in letter B and C, they're asking for different information. So we're going to continue to use this equation that we've now written. So now for letter B, it says, what was the temperature of the cake after 40 minutes? So we're going to use this equation, and we're going to plug 40 in for the little t because it's time. So I have 140 e to the negative 0.0231 times 40. And again, this is just calculator work. Make sure that you put parentheses around that entire exponent, so the 40 is being multiplied by that negative 0.0231, not by the whole thing. And when we do that, we get approximately 126 degrees Fahrenheit. So after about 40 minutes, the object has cooled down to 126 degrees Fahrenheit. So for the last one, letter C, it says, when will the temperature of the cake be 90 degrees? So now they're giving us a temperature. So now we're going to plug that in for big T. Equals 70 plus 140 e to the negative 0.0231 t. So notice this one's not just calculator work. This one I have to actually solve for. So it's very similar to that first process. So I subtract 70. So I get 20 equals 140 e to the negative 0.0231 t. And I'll divide by 140. And again, you can choose to put that as a decimal or a fraction. If you leave it as a fraction, it's 1/7. And now at this point, I need to put it in natural log form. So I have ln e of 1/7 equals negative 0.0231 t. And I know I can divide both sides by that decimal. And you should notice that the process for these problems is becoming very repetitive. So when I type this in the calculator, I get T equals 84. So this means it takes about 84 minutes to cool down, which would be roughly 1 hour and 24 minutes. So almost an hour and a half for it to cool down to 90 degrees. So we definitely are going to do some more practice on Newton's law of cooling tomorrow, and I'm going to show you how you can apply this to like a CSI scene with bodies that have been dead and for how long they've been dead for.